Well, here we go with chemistry, since it's your favorite subject. Everybody loved chemistry in high school, unless you did not have chemistry in high school. If you didn't have chemistry in high school, you're probably signed up for Chemistry 05. We're going to jump right into it today. No worries, you're going to love it. It'll be your favorite subject that you've ever had in your entire life. My advice to you is not to memorize, to understand, and come to the study sessions. Come ask me. We'll have a study session. We can draw all the atoms that you want. We can go over all of the biochemistry. You need to understand acids and bases and pH, especially for anatomy and physiology. And don't forget to ask questions. A lot of students who've had chemistry assume that they understand all of this stuff and that they don't practice at home, or they don't ask any questions just because they're a little too proud. Ask questions. Please. Please ask questions. Okay. So we're going to start with matter. Matter is anything that has mass and takes up space. For the most part, you can see it, touch it, feel it, smell it, lick it, all that good stuff. And there are 4 states of matter. Plasma is included as a state of matter, but we're not going to define that here. The states of matter that we deal with in anatomy and physiology are solids, liquids, and gas. Solids have a definite shape and a definite volume, whereas liquids have a definite volume, but they take the shape of their container. And gases vary in volume, and they vary also in their shape. They take the shape of the container that they are in. When it comes to energy, energy acts on matter, and we have energy that is potential, and we have kinetic energy, and the difference between those two would be energy is stored energy, potential energy is stored energy, whereas kinetic energy is energy in action. So an example of potential energy could be, batteries, but in the human body, potential energy would be chemical energy stored in the bonds of ATP. And ATP is adenosine triphosphate. It's the energy molecule that our body cells use. We can't use glucose directly for energy, so we use ATP, or adenosine triphosphate. I have that written down on a separate slide, so you can see how that is spelled later on. Kinetic energy, which is energy in action, is maybe say a rock rolling down a hill. It's an example of kinetic energy. Or maybe your muscles moving, or riding a bike. And if we want to take an example of kinetic energy, if we use this previous example, if we had chemical energy that was stored in the bonds of ATP, if we break those bonds of ATP and we release that energy, then that's kinetic energy. So if we want to compare the two, here is the ATP molecule. Here's adenosine triphosphate. This is how we spell adenosine triphosphate. And this is what the molecule looks like. We take adenine and we add a ribose. This is a sugar. This is a little nitrogen containing base. We take adenine plus ribose sugar and we add 3 phosphate groups to it. Here's one phosphate group, here's another, and here's another. This is where the energy is stored right here in a little covalent bond between these phosphate groups. Here's another high energy covalent bond. So we're storing the chemical energy here. Here's potential energy. Here's potential energy. They're like spring-loaded covalent bonds. So we are storing this potential energy here. And if we break this bond by hydrolysis, if we break this bond, then we release that energy, and that energy that is released can power these muscles. So this is the kinetic energy here. If we move our muscles, if we contract those muscles, that's kinetic energy. So kinetic energy, potential energy. Energy stored in the bonds, and then energy being released to move the muscles. So we've got some definitions here that we need to go over, and it's the different types of energy. We've got chemical energy, electrical energy, mechanical energy, and electromagnetic energy. These are some different types of energy that you need to know. Chemical energy is going to be energy that's stored in chemical bonds. And a big chemical bond, a big molecule that you need to know is adenosine triphosphate. So here's the spelling again, adenosine triphosphate. This is the energy molecule that our cells use. And this is what it looks like, adenosine triphosphate right here. If we break it down to release the energy, it breaks down into this molecule right here. This is adenosine diphosphate, and we release a phosphate group, an inorganic phosphate group. So it looks like this when we write it down, the little chemical formula here. Adenosine triphosphate breaks it down into adenosine diphosphate and an inorganic phosphate group. So you might see this quite often. This is stored energy, this is releasing energy, and we release energy into the environment here. In electrical energy is moving, well, if we're in a house, we're moving electricity along wires. We're not moving ions, but rather we're moving whole electrons. In your body, it differs. In your body, we're moving ions across cell membranes. That's very important. We're going to see electrical energy moving in the body all the time. So we're moving ions across cell membranes. And the big example in your body is how energy flows along neuron cell membranes or flows along muscle cell membranes. So here's a great example here. Mechanical energy, we're just going to say simply for mechanical energy is movement. Moving things is mechanical energy, and an example in your body is muscle movement. And then we have electromagnetic energy or radiant energy. And this type of energy is any kind of energy that travels in waves. And an example would be all of the energy waves that are traveling from the sun. In the next slide, I want to show you what electromagnetic energy looks like, just in case you haven't had it in a general biology class. This is a slide of the electromagnetic spectrum. And up here on the top of the slide, it's showing you wavelengths. And as we move from this side to this slide, the wavelengths are increasing in magnitude. Here we have short wavelengths, and here we have very long wavelengths. And if we have a very long wavelengths, these wavelengths don't have much energy on this side of the electromagnetic spectrum. And over here, these wavelengths that are very short, they have a lot of energy. So we see gamma rays, X-rays, and ultraviolet light. These have shorter wavelengths and they have a lot of energy. So you know that gamma rays and X-rays can damage your cells, so can UV radiation. But over here, radio waves and infrared light, they have very large wavelengths. They can't damage your cells. And here's visible light. Visible light is just very small part of the electromagnetic spectrum. This is the part of light that we see. You've probably heard of Roy G. Biv. It's backwards here. Red, orange, yellow, blue, indigo, violet. Those are the colors of the rainbow. This is 400 to 700 nanometers. This is the part that we can see on the electromagnetic spectrum. Notice that UV radiation is the wavelengths on UV radiation is smaller than visible light. We can't see UV radiation, UVA rays, UVB rays. This is why we wear sunscreen, to protect us against this radiation that's smaller than visible light. These wavelengths can penetrate our skin, and then they can go right through our skin cells, right down to our DNA, and they can damage our DNA. So that's why you're supposed to wear sunscreen, to prevent aging and burning and damaging your DNA, because these wavelengths have enough energy to damage your DNA. This is the electromagnetic spectrum, just in case you've never seen it. Okay, up to the end of this section. Those types of energy, chemical energy, electrical energy, mechanical energy, and radiant energy, they can be converted from one type to another. Say you walk into a room and you flip on a light switch. You are switching electrical energy to light energy. You're doing an energy conversion. So we need to talk about these laws of thermodynamics. You're living in a universe where energy cannot be created or destroyed. There is a constant amount of energy in the universe, and that brings us to the first law of thermodynamics, which states that energy in the universe cannot be created or destroyed. Oops, that should say or destroyed, but one form of energy can be converted to another form. For instance, like my last example, electrical energy can be converted to light energy, or for instance, in our muscle example, ATP energy, which is chemical energy, can be converted to mechanical energy of your muscles moving. One type of energy can be converted to another. So that's the first law of thermodynamics. Energy conversions can occur, but all energy in the universe will remain constant. But there is a consequence of converting one energy type to another. When you convert one type of energy to another, we all know when we work out, we're going to release heat. When you convert one type of energy to another, you're going to go down in the quality of your type of energy. You're going to lose heat to the surroundings, and heat is a very low quality type of energy. So that is, you're going to dissipate heat, and when you convert one type of energy to another, you're going to lose heat to your surroundings, and the quality of your second type of energy is not going to be so great. So that brings us to our second law of thermodynamics. While the quantity, the amount of energy remains the same in the universe over time, the quality does not. So while we're doing all these energy conversions, we're losing heat to our surroundings, and basically our quality of energy is getting less and less and less and less and less. So that brings us to the word entropy. Entropy is a measure of disorder, and so we're becoming more disorganized over time. So in the human body, the way we have to fight entropy, disorganization, is we have to constantly put energy in, energy in, energy in, energy in, energy in. And that's about it. It brings us to the end of this section.